My favorite chapter. All right. So why? Because it's Oak Ridge. It's the whole reason why Oak Ridge exists. First target. I can explain what ionizing radiation does to living tissue. We're going to continue to talk about radiation. We need to refresh our memories about something. What is an isotope? Who remembers? What is an isotope? You? No. No. Yes, Jasper? Awesome. Samples of the same element. So they have the same number of protons. They have to have the same number of protons, but they have different numbers of electrons. It's kind of like, it's ice cream, but it's a different flavor ice cream. Think of it as different flavors of each element. Yes, sir. Not now. We're doing this now. What are radioisotopes? Okay, well, an isotope you now know. A radioisotope will be one that is unstable. Did we go through we went through the metaphor, right? That was Davino. Okay. So if Davino is an isotope, and let's say Maddie is an isotope of the same element, then Davino would be a radioisotope, while Maddie would not, because Maddie will never ever break down into will break off small particles and become something new. Freddie does. That makes him a radioisotope. Okay, some of those teeny tiny particles that come out are alpha, beta, gamma. So what happens if you're hit with ionizing radiation? Think, ionizing radiation. My honors chemistry students have trouble with this. If you're ionized, what do you become? If you are ionized, what do you become? An ion. Yes, an ion. Okay. If you become an ion, it changes you. So atoms, when they become ions, can be changed. And if you change an atom, you change the way it works. So if you are hit with ionizing radiation, most of the time it goes straight through you. Okay? Most of us, we are hit with ionizing radiation every day, probably every hour, probably every few minutes you're hit with ionizing radiation. And most of the time it goes straight through you. If it doesn't go straight through you, it may kill one of your cells. It may kill one of your cells. That's actually not bad, because if it kills a cell, you've got more. So, if you're lucky, it goes straight through you. If you're not lucky, it may kill one of your cells, in which case, you've got more, as Robert says. All right? If you're really unlucky, it may change the DNA in some way. If it changes the DNA in some way, that particular cell may start producing something else instead of producing what it's supposed to produce, which, because it's just that cell, may not necessarily be a game changer, but you may have some physical aspects of physical problems because of it. All right? So that's if you're really unlucky. If you're really, really unlucky, then what could happen is it could change one of the atoms that make up the DNA that's in charge of replication. It could change it. And if it changes it, it could change the way your DNA replicates. And if it changes the way your DNA replicates, then you could have cancer. Folks, normal people will look at you when you're 86 years old and you die and go, well, he died of old age. But nuclear chemists will look at the same people and say, he died of nuclear radiation. Why? Because every day, every hour, every few minutes, you are exposed to radiation. Most of the time, it doesn't affect you. The more time flitters on by, the better the chance that you're going to be unlucky. So when you die at 86 and you die of some form of cancer or you die of some kind of disease, chances are at 86, Jasmine, you will have died of exposure to radiation. And there ain't a dang thing you can do about it. There is no way to hide from ionizing radiation. Now, you can limit how much ionizing radiation you're exposed to. You know, you don't have to work at ORNL. Even if you do work in ORNL, you don't have to work with ionizing radiation. Okay? So if you do, you are going to probably be making more money than others because you know ahead of time that you are probably taking some years off the end of your life by exposing yourself to more radiation than is normal. Okay? Airplane pilots, they know this. They know this. They make a lot of money. Stewardesses, I'm sorry, they're called flight attendants, right? Flight attendants, they know this. What's going on? Well, they're very high in the atmosphere. So they're being exposed to cosmic radiation. Cosmic radiation. What? They get it. I'm sure they get a decent amount. Okay. Pilots probably make more because, after all, pilots have to probably undergo more education, right? But they understand. I guarantee you that before they become a flight attendant, they sign a paper saying that they understand that by spending a large portion of their working day up in the upper atmosphere, that their chances of getting cancer are going to increase. What about people that work with X-ray machines? They can take, they do take a lot of precautions. One of the biggest precautions is they usually leave the room or they go behind a shield. Yeah. So there's no way around it. You're going to be exposed to radiation. So it's important to learn what kind of radiation we are exposed to. We need to be able to detect when we are being exposed to ionizing radiation because our bodies cannot do so until it is too late. When your hair starts to fall out, it's too late. And I'm not talking because, you know, your dad went bald. I'm talking about your hair is falling out because of radiation. What device was first used to detect radioactivity? It's called a Geiger counter. A Geiger counter. Is this fill in the blank?
Yeah.
Okay. When ionizing radiation enters the counter's tube or probe, it causes the gas that is stored there to become ions. Now the gas has a positive charge. It can conduct electricity. When it does this, the counter registered a count. The unit of measure is counts per minute. So here it is. What you're seeing there is that tube. That tube contains that argon gas, and whenever any radiation comes in through that opening there, it's going to zap some of that argon gas and cause it to become an ion. It ionizes it. Watch.
Geiger-Müller or GM counters are one of a class of gas-filled radiation detectors that operate by using the ionizing nature of alpha, beta and gamma radiation. The GM tube is a sealed metal cylinder containing a low-pressure inert gas such as argon or neon. A thin metal wire runs down the centre of the tube, which is electrically insulated from the outer cylinder at the rear of the tube. The front of the tube is sealed with a radiation window that is specific to the typical radiation to be detected by the counter. For example, a thin mica window is used if the tube is to be sensitive to alpha particles and low energy beta particles, both of which have low penetrating power. A thicker window, or a different material, such as glass or a thin sheet of metal, is used for high energy beta particles, while for gamma rays the tube is often sealed without a window. In such tubes, the detection occurs when the high energy photons liberate electrons from the tube's outer wall. The inner wire and the outer cylinder are maintained at a potential difference of about 1 kilovolt, and in the absence of radiation, no current can flow through the inert gas between the central anode and the outer cathode. The connections are made via wires into a connecting housing that fits over the rear of the tube. An outer tube guard will typically screw onto this to protect the actual GM tube. This tube guard can be open at the end or be covered by an end cap energy filter to change the energy and particle sensitivity of the device, or, if a carefully calibrated design is used, allow for ambient dose measurements rather than ambient count measurements to be made. The wires connect the tube to the control electronics, which supply power, perform the counting operations, and provide other functions such as conversion from counts to dose, data logging, data averaging, and driving the display. The tube works on the principle of gas amplification.
Here we go. Here comes some ionizing
Incoming
radiation.
ionizes some of the inert detector gas, resulting in a free electron and a positive.
Okay, so what's going to happen is this electron is going to be attracted to the wire, and that's going to alter the voltage. And you have it. Geiger counter is basically a voltmeter. So when it changes the voltage, the current, then the voltmeter will be able to figure that out, and it tells you that something has happened. Next week, when I bring that Geiger counter in here, it'll tell you by going blip, 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 blip. Terribly annoying, wasn't it? Yeah. All right.
Positively charged ion. The electric field inside the tube attracts the charged ion to the outer cathode, while the electron is attracted towards the central anode. The charge migration in the tube leads to a reduction in the...
Okay, so I showed you that in order to let you see that, a lot of these gadgets that are all around you are not as complex or as mysterious as you might think. And a Geiger counter is very useful, but it is not that complex. What kind of radiation can a Geiger counter or can Geiger counters detect? Alpha, beta, gamma. In a couple of weeks, when we work with the Geiger counter, we're going to have to determine background radiation. What is background radiation? Well, believe it or not, I let you know this. Right now, in the last 10 minutes, you've probably been exposed to some kind of ionizing radiation. It's the stuff that's naturally around us. We can't run away from it. We can't protect ourselves from it. It is just naturally around us. Unless you're going to wear a very, very, very thick suit of lead, you're going to be exposed to background radiation. Okay? Even if they were to put you in a lead box, they still have to feed you, and the air is still loaded with radioactive particles. So no, there's no way around it. You're going to be exposed to background radiation. How do you factor out when you're measuring radioactivity? We just subtract it out. So if we try to determine how radioactive Jasmine is, and she reads 25 counts per minute consistently for a 10-minute count, and we find that background radiation on the average is 24, guess what? She's not radioactive. It's just the background radiation. That's right. Where this would become more significant is if you're measuring something and it's 10,563 and the background radiation is 24, you could say, well, of that 10,563, 24 of it is background. Subtract it out. Subtract it out. So when at ORNL they work with radiation, they're going to be able to tell the people that are working with the radiation how many rads they're being exposed to. That is radiation absorbed dose. That's a numerical value. It means something to them. Another unit is used is a gray, but for us the REM, the REM, is the most important. Okay, it accounts for the amount of damage it can do to you. So we are exposed, they've been able to calculate how much REMs we're exposed to. And for most of us, we're talking about millirems. So we're not even exposed to whole REM. You would have to have several chest x-rays a year to get up to a whole REM. Yes, Joey. No, Joey. Why might radiation exposure level standards for some individuals be different from those for the general public? Yes. Yeah. Right. If they're going to be exposed to greater amounts of radiation than background, especially at ORNL or Y12, they're going to let them know. And they're going to sign a contract. They will know that this is going to do damage to them and how much they're going to do damage, how much. So the EPA is going to set a limit for them. There have been these workers that have gone to work January 2nd, received enough radiation that day to hit that limit, in which case they're not allowed to work there anymore. They have to be placed in a job that does not have a higher amount of background radiation or radiation than background. Okay, that is possible. All those workers at RNL have limits, how many millirems, how many REMs they can be exposed to in a year. And that's set by the EPA. Now the EPA is going to have limits for us, but those are going to be far lower because we don't work with radiation. Yes? So what happens if they do exceed that limit? They can't lose that job, but the company, or RNL cannot allow them to be at that job. They're going to put them probably working in a place that there is no radioactive material at all. Right. I mean, there's cleanup teams, and this is the ones that are going to get this, the cleanup teams, and they may go years without hitting that limit because there weren't any big spills, but it only takes one big spill, and then they may have to expose themselves. Now, what does that do? Does that damage them? Yeah, they can get cancer from that. Okay, they know that. They get paid. They get paid well. Just like football players. Robert wants to be a football player. If he ever makes it to the NFL, he will be signing as part of his contract. He will be signing and understanding that this is a contact sport and that a cumulative damage to his brain could eventually cause him to develop Alzheimer's like characteristics. It's called CTE. I don't remember what CTE stands for, but it's called CTE. And yeah. Name some of the natural sources of background radiation: cosmic rays, radioisotopes in rocks and atmosphere. Name some. For example, Robert back there is probably being exposed to more radiation than Robert and Zach are probably being exposed to more radiation than the rest of us.
They're closer to the window.
Cinder blocks. The cinder blocks are going to have invariably some heavy metals in there, and some of those heavy metals may be radioactive. No, because it's just made of I mean, there's going to be some, but not as much as a cinder block. It's just particle board. I mean, not particle board. Sheetrock. Yeah, it's just a form of no, it is a form of concrete, very thin pieces of concrete. Now, what are some unnatural sources of radiation? Fallout from nuclear weapons testing. We don't have to worry too much about that because we live here. If you lived in Nevada, you would worry. Thank you. Robert Hill, student service. Increased exposure to cosmic rays due to air travel. You get pneumonia and you have to have a series of x-rays for your chest. That might do it. And of course, there's going to be radioisotopes. A lot of tests. For example, my daughter she got gallbladder problems, and they had to give her radioactive gadolinium in order to see whether her gallbladder was working. And I mean, and they let us know that. They go, we're going to expose your daughter to unnatural levels of radiation. Okay, chances are she will be fine. But if we don't figure out whether this gallbladder is working or not, we'll have to cut her open and then investigate. Okay, so your choices are increase your chances of getting cancer sometime in the future or getting cut open now just to see whether your gallbladder is working or not. Okay, so we opted for blast her, give her some radiation. So most of our radiation is going to come from radon, which is a colorless, odorless gas that is a result of uranium decay. We'll talk more about radon, but most of our radiation comes from radon. Other natural sources, 26%, and then look at, this is what we're responsible for as mankind, all right? Don't go to bed and snuggle with your smoke detector. That is the most radioactive part of your house. Okay? So, you do that? Okay, Freddie, stop doing that. Don't snuggle with your smoke detector. Okay, that smoke detector, if you're that scared of being involved in a fire that you go to sleep with a smoke detector, it would probably be better to put it somewhere so that it'll let you know that the fire is getting there before it gets to you. Okay, stop snuggling with your smoke detector. Folks, you're all radioactive. So the next time somebody comes up to you, oh, you're from Oak Ridge, you glow in the dark, don't you? You look at them and go, first of all, very few elements glow in the dark, and I have not been exposed to any of them. Second of all, we're all radioactive, and so are you. These are all the places in your body where they will find radioactive particles. What is the estimated background exposure in a year? 135 millirems. Just millirems. It doesn't even reach a whole rem. Yes. What level of radiation is considered safe for the average person? 170. No, that's a year. A year. What sources of radiation do we have a choice in, whether we're exposed to them or not? No, not what types of radiation. What sources of radiation? X-ray. You can look at your dentist and go, you ain't getting that stuff close to me. You're not going to take a picture of the inside of my mouth. No way. Okay, as you're laying there writhing in pain, you can look at the doctor and go, no, don't irradiate me, cut me open, cut me open. You have the choice. You have the choice. X-rays and other medical procedures. What happens if you're exposed to a low level of radiation? Well, very small molecules are going to be harmed and your body will repair it. But what eventually will kill you, folks, once again, I hate to be morbid, but you need to know what will kill you if you die of old age. What will kill you is the cumulative effect of that little bit of radiation that you will receive your entire life. What happens if you're a radiation worker or you're working near a nuclear power plant and you receive a high level of radiation? It's going to damage a lot. Now, people survived Chernobyl and they're still alive today. Most of them died. Chernobyl was that terrible disaster in Russia where a nuclear reactor exploded. What happens if your DNA and your cells are damaged? It either kills the cell or causes it to make proteins that it normally doesn't make, or it can give you cancer. What are some diseases that are supposedly caused by radiation damage? Leukemia, anemia, heart-related problems, and cataracts. Cataracts is probably leukemia. Yes, little white spots on your eyes, that's cataracts. If you've got an old dog and the eyes look cloudy, that's yes, they can fix that. Are we safe from low levels of radiation? To tell you the truth, probably not, but all that means is you're going to die at some point. How many millirems are we believed to receive a year? 150. We went over that. Okay, dose, exposure time, area time, all those are factors that are important. How about this one? 0 to 25 rems. Remember, we get 135 millirems, so we don't even get to 1. So 0 to 25, you can't tell. But if you're a radiation worker and you get over 25, you may see a small decrease in white blood cells, causing lowered resistance to infection. 50 to 100, it kills your immune system. 100 to 200, it's called radiation sickness, nausea, vomiting, hair loss, and your red blood cells die. 200, 300, you are bleeding inside. Oh boy. 300 to 500, 50% of you will die in the next few weeks. Over 700, you will die. You will die. Okay? For that one, you probably need to be near enough to a nuclear explosion. All right, alpha rays. Get ready to write again.
Ernest Rutherford confirmed that radioactivity involves 3 different types of radiation: alpha, beta, and gamma. Alpha radiation consists of positively charged helium nuclei, that is, 2 protons and 2 neutrons. The radioisotope americium-241, used in smoke detectors, emits alpha particles. The parent nucleus contains 95 protons and 146 neutrons, making a total of 241 nucleons. When an americium atom decays by ejecting an alpha particle, the remaining nucleus has only 93 protons. This is a new element called neptunium-237. The decay equation looks like this. Neptunium-237 has 2 less protons, 2 less neutrons, and 4 less nucleons overall. Positively charged alpha particles are affected by magnetic and electric fields, but because they are relatively heavy, they are only weakly bent or deflected. They have low penetrating power and are absorbed in a few centimeters of air or by a sheet of paper.
Okay, so what is an alpha particle? It is 2 protons and 2 neutrons, just like the nucleus of a helium ion. We're going to look at a beta particle here in a second. What is a beta particle? How does it compare? It is 8,000 times larger, but can only travel just a few centimeters, and your skin will stop it. Your dead layer skin, your dead skin layer will stop it. So you have enough dead skin cells to stop alpha particles. Outside of your body, they're perfectly safe. Inside your body, though, not dead, but they can hurt you. They can hurt you. And remember, it's only if you're really, really unlucky that it causes cancer. So what you have here is radium going about minding his own business, and then Davino, there is a bright light. There is radon. Now radon is staring at us, and this is what hit poor Maddie. Okay, a tiny little chunk of his nucleus. Where can alphas cause great damage? Inside your body, your lungs. Easiest way for it to get in there is through cigarette smoke, marijuana smoke. So you smoke pot, you smoke cigarettes, a lot of that stuff contains radionuclides in the plants, and that just gets stuck. That smoke gets stuck in your lungs and just sits there until it goes off, releasing an alpha particle. Give an example of a reaction where alpha is emitted. Let me give you the bottom numbers because those are useful as well. I should have given you the bottom numbers here. So radium is number 88. This is number 2, and this is number 86. You're going to love how to balance these equations because all it is just addition and subtraction. Imagine the arrow means equals. Does 226 equal 4 plus 222? Does 88 equal 2 plus 86? Congratulations, you just balanced your first equation.
The second type of radioactive decay is beta decay, which simply emits electrons. It has somewhat higher energy than alpha radiation, but it can still be stopped by a sheet of aluminum foil or even the top layers of your skin. So that thorium-234 that formed when uranium underwent alpha decay, it can continue to decay on its own, and when it does, it undergoes beta decay, releasing an electron and an atom of xenon. Notice that, again, the way we write this is a little different. Even though the thorium emits an electron, we don't use the usual symbol for electron. Instead, we write it in nuclear notation form with the mass number at the top and the atomic number at the bottom. Since it's an electron and not a proton, we put a -1 for the atomic number. That probably seems a little bit weird right now, but next week when we talk about nuclear equations, you will see why it is useful.
Wait, hold on. Hello, this is Marino. Yes. Yes. Excellent. Okay, I'll probably pick it up Friday afternoon. All right, thank you. Bye-bye. What a coincidence. My Geiger counter and all the radioactive sources is ready for me to pick up tomorrow afternoon. So on Monday, I'll have radioactive sources here to expose you with. What are beta particles? Fast-moving electrons emitted from the nucleus during beta decay. Fast-moving electrons emitted from the nucleus during beta decay. It is much, much smaller. I mean, much smaller. So it doesn't do as much damage but it can damage you from the outside. It can give you skin cancer. It can give you skin cancer. So it can penetrate your skin a little ways. It's teeny tiny. I like to think of it as either having a bowling ball loose inside your body or having a BB. Inside your body, you do not want a bowling ball loose. Okay? Outside your body, what happens if you get hit with a bowling ball? It may hurt, but it's not going to penetrate your skin. What if you get hit with a BB? It may penetrate your skin a little ways. Okay? So what exactly happens during beta decay? A neutron is transformed into a proton and electron. The proton stays in the nucleus and the electron is ejected, becoming the beta particle. Okay, write this down as you hear my story. I always, when it comes to this, I remember the movie Twins. In the movie Twins, these eugenicists, these are people in the 1950s who were trying to create the perfect man. What they found was a genetically wondrous woman, artistic, extremely intelligent, very musical. And they took an egg from her, and then they combined the DNA of a super athlete and a super genius in hopes of making a superhuman. So they implanted the egg, and she became pregnant. 9 months later, instead of having one baby, she had two. She had this beautiful, beautiful, strong, extremely intelligent baby boy, and this scrawny, ugly little baby boy as well. What they realized must have happened is that when the egg implanted, it split into two to create twins. Okay? Arnold Schwarzenegger got all the good genes, and Danny DeVito got all the bad genes. So when they were born, they shipped Danny DeVito to Chicago to an orphanage where he grew up to get a nun pregnant and become a con artist. And back in the island in the South Pacific, Arnold Schwarzenegger was trained with a world-class education, and he became a perfect man until he accidentally found out that he had a twin brother. So he decides to travel to the US to find his twin brother. And the rest of the story is the movie. Okay, it's a really cute movie. So I like to think of this as that neutron is the original egg. And then it becomes a proton, which is Arnold, and then the that's left over is the beta particle. Okay? So one neutron, one zero neutron yields 1 proton and 0 -1 electron. Let's see if this adds up, and we'll finish right here. Does 210 equal 210 plus 0? Man, you guys are good at math. Does 82 equal 83 minus 1? All right, let's stop it right here. Here we go, 16. How do these guys usually leave the nuclei? In an excited state, so lots and lots of energy. What is usually given off along with particles? Remember from our analogy, every time Freddy would regenerate and become somebody new, there was always a blinding light. That blinding light is the energy that oftentimes is emitted along with the particles. Energy in the form of gamma radiation. In the form of gamma radiation. How does gamma compare with alpha and beta? Well, it's just pure energy. So it's not made up of particles. It has the greatest penetrating power because it has no mass, but it doesn't do as much damage. Gamma radiation source that I will bring next week will travel quite a few meters and hit us all. Go straight through you. Okay? They may set off something that you won't find out about until you're in your 80s. And by that time, I'll be dead. So there won't be anything you can do about it. No, gang, the gamma radiation it's outside of your body. If you're exposed for a long period of time, will eventually start doing damage. But most of it goes straight through us. You won't be exposed to it for very long. Once a year, and I move it away from me. I mean, I may be exposed to it for a few minutes. Once a year, I'm okay. That's probably more, that's not as much radiation as a chest x-ray. None. I have lost 48 pounds.
Gamma radiation is a form of electromagnetic radiation, like radio waves, heat, and visible light. It is found at the highest frequency end of the electromagnetic spectrum, after X-rays. Gamma rays are produced in the nucleus as part of a rearrangement of energy levels after the emission of an alpha or beta particle. For example, when a uranium-238 nucleus releases an alpha particle and decays to thorium-234, a gamma ray is also produced. Having no charge, gamma rays are unaffected by electric and magnetic fields. They have low ionizing power compared to alpha and beta particles, but being photons or packets of electromagnetic energy are the most highly penetrating of the nuclear radiations. Gamma rays are mostly, but not completely, absorbed by a lead shield several centimeters thick.
Okay, so in review, alpha particles are made up of 2 protons and 2 neutrons. Big old suckers. Well, comparatively speaking. Beta particles are teeny tiny little things that kind of are the same size as an electron, though it's not an electron, but we make believe it is just to help us. And then gamma radiation is pure energy, not made up of particles. Alpha can be stopped by paper. Beta can be stopped by a thin piece of aluminum, and it's going to have to take some lead to stop gamma. Now, I want to introduce you, you'll need to add this to your notes, to a couple more particles. So let's review. You might want to recreate. You're going to have to memorize this chart. And it's an easy chart. You're just going to have to memorize it. Okay, that is the symbol for alpha, and it's 4,2 helium. And it has the least penetrating power. And of course, it is called ALPHA. A B with a little squiggly on it is called a beta. and it's a 0, -1 E. Now, there are such things as positive betas. They are called positrons because it's kind of like a positive electron. Does that make sense? They would be called positron? Yep. And oops. Oh, I pushed a button here. I could see myself on the screen. 1, 0, neutron. So a neutron can be spat out of the nucleus as well. Yeah, that's like an N, like a italics N. I'm sorry, I'll do it again. That's a 1, 0 neutron. And then finally, what looks like a Y is actually the letter G in Greek. And gamma is the most penetrating. Can I see your homework a second? Can I see your homework a second? Yes. Okay. We need to continue going. You now know how to balance equations, but the nuclear equations are different. You have to account for all the particles that make up the atoms, not just the atom itself, but they're really, really easy. Let's practice. Okay. What you have to do is make sure the top numbers and the bottom numbers add up. It's that easy. Okay? So 212 equals 4 plus what? In other words, 212 minus 4 will give you what goes in the blank. 208. Let's raise our hands so that everyone has a chance. 208. Does that help us identify what this thing is? No. We need the bottom number for that. Here we go. 84 equals 2 plus something. So the easiest way to do this is go 84 minus 2. Canaan, 82. And look on your periodic table, who is number 82? What? Lead? All right. Ryan, since you did such a great job figuring out that that was lead, you can do the next one. 143 equals what plus 142? In other words, 143 minus 142 is 61 equals what plus 60? In other words, 61 equals minus 60. All right, so who is number 1, Ryan? Hydrogen. So far, so good? Not that hard. Maddie, thank you for volunteering to do the next one. 253 plus 4 is what? Maddie. 253 plus 4 is what? Okay, so 257. So we need to make sure that 257 adds up. So 1 plus what is 257? So 256 plus 1 is 257. All right. 99 plus 2 equals, pardon me? 99 plus 2 equals 92. 101. 101 equals 0 plus what? That's right. So who is number 101? Mendeleev. You have faced many difficult things, but this ain't one of them, is it? All right, these may be, of all the easy ones, this may be the harder of the easy ones. Okay, because here they're looking for how many of these do you need in order to make sure that everything balances out. All right, somebody new, somebody like Elaine. 238 plus 1 is what? $239. All right, on this side, ignore this for now, okay? Ignore it for now. You're going to have to subtract 110 and subtract 126. Should give you a whole number somewhere. Aha, 3. So what number is missing here that would give you the 3 you need? Let's make sure this works. 92 plus 0 is, Elaine, 92 minus 0 minus 36 minus 56. It better equal nothing. Does it? See how we did that one? You just have to find what number fits in there that makes both sides equal. Yes? Three zeros is what? 0. So no, it would not. No, 3 ones is what? 3. What was the difference between those two sides? 3. Now it's equal. You have to make sure they equal out. How about this one? Reagan, thank you for volunteering. 37 equals 37 plus what? 18 equals 19 plus what? Exactly. No, you're absolutely right. Look on your chart. What is the symbol for 0, negative 1? Beta. So what's the symbol? What symbol do I put here? No. The nuclear symbol. The B is the abbreviation. Thorium-232 undergoes radioactive decay until a stable isotope is reached. Complete the following reactions for 232. These are 11 steps beginning with alpha decay and the product becoming the reactant for the next reaction. All right, so Freddie Davino, 232 equals 4 plus what? 90 equals 2 plus what? Who is 88? Okay, this one's going to be beta decay. So it was 228, right? What was the bottom number? 88 radium. Will undergo beta decay. Malachi, what does beta decay look like? What's the nuclear symbol for beta decay? What? Yes, it's a B, but that's the abbreviation. What is the nuclear symbol? Top number, bottom number, letter. Okay, good. So that means beta decay. All right, so here we go, Malachi. What plus 0 is 228? What minus 1 is 88? Who is number 89? Actinium? Okay. Good job, Malachi. Emma. So let's start with what Malachi ended up with. And it's another beta decay. So that means, what is it producing? What little particle is it producing? Okay, and what are the numbers? Here we go. What plus 0 is 228? What minus 1 is 89? Who is 90? Excellent. AC, now we get a little change. 22890 undergoes alpha decay. So what does the particle alpha look like? 4,2 helium. All right, what plus 4 equals 228? What plus 2 equals 90? Who is number 88? All right. AC is going to hand off radium to Joey. Joey, alpha decay means what kind of particle is released? It is indeed, sir. What plus 4 is 224? What plus 2 is 88? Who is number 86? Very nice, very nice. Cassidy. So it was what? I already forgot it. 22086. Another alpha decay. Cassidy, what particle is released? That's beta. Very good. What plus 4 is 220? What plus 4? What plus 2 is 86? Who's 84? Zachary, it's up to you, bud. 216 PO undergoes alpha decay. What plus 4 is 216? What plus 2 is 84? Who is 82? Okay, so I think you guys get the picture and the pattern. So I will let you do the rest there. I will let you do the rest there for now. So I'm going to stop right there.